Hello everyone, thank you for coming to our poster on Matthew's correlation coefficient laws for deep convolutional networks, application to skin lesion segmentation. I am Kumar Abhishek, a first-year PhD student in the Medical Image Analysis Lab at Simon Fraser University in Canada, and this is a work with my supervisor, Professor Kassan Homarne. Class imbalance is a prominent issue in medical images, where some classes occupy larger image regions than others. This is also the case with skin lesion images, where, because of considerable variations in skin lesion sizes and lesion acquisition setups, skin lesion images, be it clinical or dermoscopic images, often contain a large fraction of healthy skin. These can be considered as the background or true negative pixels for lesion segmentation tasks. It has been shown in previous works that the values obtained from cross-entropy-based loss functions are not sufficiently indicative of segmentation quality, and therefore overlap-based loss functions are preferred. However, popular overlap-based loss functions for segmentation, such as dice loss or intersection over union or IOU loss, do not take into account the true negative pixel predictions. To address this problem with the existing popular overlap-based segmentation loss functions, in this work, we propose a novel differentiable overlap-based, metric-based loss function which takes into account the true negative predictions and thus penalizes misclassification of the background pixels. This loss function, as we show in our results, handles class imbalance better and yields a better trade-off between sensitivity and specificity of the predictions. Consider the skin lesion image segmentation example. The ground truth lesion segmentation mask boundary is indicated by the black contour, and the yellow contour indicates the predicted lesion segmentation mask. As such, we can partition the pixels in this image in 4 distinct categories depending on their class and the correctness of the predictions. This is shown on the right, where the 4 colors denote the true positive, true negative, false positive, and false negative predictions. That is, the 4 entries of a confusion matrix. Notice how, despite the lesion being large, the true negative pixels denoted by gray occupy a considerable fraction of the overall image. In this work, we use the Matthew's correlation coefficient, or MCC, to construct our loss function. It has been shown in previous works that MCC is an informative and an optimal metric for skewed distributions and imbalanced classes. Here is the expression for MCC, and we can see that it uses all the entries in the confusion matrix, including true negatives. MCC takes values from -1 to +1, where -1 denotes a completely disjoint prediction and +1 denotes a perfect prediction. In order to convert this metric into a differentiable loss function, we use soft probabilistic labels obtained from a deep neural network-based segmentation model to calculate the MCC, and then define the MCC loss as 1 minus the MCC metric. To evaluate the performance of the proposed MCC loss, we compare skin lesion segmentation models trained using this loss function against those trained using the DICE loss function. We use the popular unit architecture for our segmentation models, which features an encoder-decoder design with skip connections. While training, we use data augmentation on the fly by randomly applying horizontal and vertical flipping and rotation from -45 degrees to +45 degrees. In order to perform an extensive evaluation, we use 3 skin lesion image datasets: the ISBI ISIC 2017 Skin Lesion Segmentation Challenge dataset, the DermoFit Image Library, and the PH2 dataset. The ISIC 2017 dataset has a held-out test partition of 600 test images, whereas for DermoFit and PH2 datasets, we partition them into training, validation, and testing splits and held out 390 test images for DermoFit and 60 test images for PH2. As you can see on the right panels, models trained with MCC loss are able to segment skin lesions more accurately than models trained with DICE loss. All but one metrics are higher for models trained with MCC loss. The only exception to this is the specificity of the DermoFit dataset, where we observe that the model trained with MCC loss yields a superior trade-off between sensitivity and specificity. We also generate kernel density estimate, or Kde plots, for these metrics to show that models trained with MCC loss produce higher peaks at higher values, thus indicating larger densities. We note that all the improvements in Jaccard index are statistically significant. Finally, We would like to highlight that the segmentation results achieved using the MCC loss function for the ISIC 2017 dataset are within 1% of the top 3 entries on the challenge leaderboard, despite not using any pre or post processing, not training on external data, or leveraging ensembles of prediction models. Here are the qualitative results for the models trained using MCC loss and dice loss functions. The first 2 rows show images from ISIC 2017 dataset, the third and fourth from DermoFit dataset, and the last 2 rows from PH2 dataset. We see that for the first 2 and the last rows, the lesions are comparatively small in size and background pixels occupy a large fraction of the image. These images capture a wide variety in the appearance of the lesions, such as their shape and size, lesion contrast with the surrounding healthy skin, and the presence of artifacts such as markers and dark corners. We see that with the MCC loss, the lesion segmentations are more accurate while also generating fewer false positive and false negative predictions. Here are the quantitative results for the models trained using MCC loss and dice loss functions. As mentioned before, all metrics except one are higher for models trained with MCC loss, and the only time when it is not the case, the model trained with MCC loss achieves a better trade-off between sensitivity and specificity. We see that the improvements in Jaccard index are statistically significant, as denoted by the asterisks. These are the Kde plots generated using an Epanechnikov kernel to estimate the probability density functions of the metrics. The plots have been flipped to the observed values, and we see that models trained with MCC loss, that is the blue curves, yield higher peaks indicating higher densities at higher values. To conclude, we proposed a novel differentiable loss function for binary segmentation using the Matthews correlation coefficient metric, whose formulation includes a penalty for misclassifying the true negative pixels. We showed the superiority of the proposed loss function over the popular dice loss by evaluating on 3 skin lesion segmentation datasets and observed that using the MCC loss significantly improves the segmentation performance while also achieving a better trade-off between sensitivity and specificity of the predictions. Finally, we note that this loss function can be used for any binary segmentation task and is not limited to skin lesion segmentation. In the future, we would like to generalize this loss to multiple classes and evaluate on more segmentation model architectures and medical imaging modalities. Here are the references used in this poster, the last 2 of which discuss some meritorious properties of Matthews correlation coefficient as an optimal metric for designing classifiers for imbalanced classes. We are grateful for the funding from NSERC and CIHR and for the computational resources provided by NVIDIA Corporation. Thank you for visiting our poster. Please contact me if you have any questions about this work or if you would like to talk about anything. Please scan this QR code for the PyTorch code for this project, which is publicly available on GitHub. Please visit our lab's website to see more of our work. Thank you.